7. Hello and welcome back to Calculus 2 sections 12.2 and 12.3 on polar coordinates. A lot of your Calc 3 will depend on this. We are going to take a look in the first part, mainly what they are and which they work with functions and so on, and then calculus of polar coordinates in the second part, where we get to differentiate and integrate in what we say polar domain. So you are used to, hold on, there we go. You are used to XY rectangular coordinate system, and the reason why it's called rectangular is when you pick a point somewhere, x, y, that point creates a rectangle like this, and you can follow x units on x-axis and then parallel to y-axis y units to get to that point. Alternatively, you can also follow y units first and then x units to get to the same point. So whether you take the path along x and then the y, or along the y-axis and then x, it doesn't matter, but we will always list the x-coordinate first and the y-coordinate second. We can have thru-dimensional space when you add z. We live in one right now. The first lecture of Calc 3 will tell you that you get to pick in a classroom along one wall to have x and the other one to be y, and then going up in a corner is z. So you can have this as a thru-dimensional, 4-dimensional, 16 dimensions if you want, because every time you introduce another line with another variable will be counted as a dimension. So this system is known as rectangular coordinate system, and it's what you have been using so far. Now, to introduce polar coordinates, we are going to use circular motion inside the xy coordinate system. So the rectangular coordinates are r, theta. R would be the radius and theta is the angle. So if I have a point 3 and pi over 3, let's say, I can graph that point in this system by, it's still xy here and here. What I do is I measure 3 units on the x-axis first. I'm measuring positive 3 because I have positive 3. If it's a negative 3, you would go on negative x. And then I find where my angle pi over 3 is, which is 60 degrees. And then I'm going to take this 3 and just swing that one to make 3 units on this blue line. And this point here is 3 pi over 3. So what you do is you graph whatever radius you have, whether it's positive side or negative side, and then you swing that for the angle. some kind of a guide, like a formula, I guess, or whatever, a diagram. You will have your positive R values graph this way, and then you will have your positive thetas counted that way, or your negative thetas counted this way. Similarly, the other side, you will have your negative R's graphed this way. Your positive thetas will be going always counterclockwise, and your negative thetas are always going clockwise. Hopefully, you still remember from your pre-calculus course that positive angles go that way. Well, look, both of my positive thetas are going in a counterclockwise, okay? So that's something that is important. So now this is your formula, or whatever you want to call it, on how to graph points in polar coordinates. So now I can challenge you guys with -4 pi over 6, let's say. And you should be able to graph this on your own now, observing the diagram above. No pressure, you have 18 seconds. We are going to start by getting -4. 1, 2, 3, -4. So go the radius out to -4. And then find 30 degrees pi over 6 in a positive way. That's this way. And then we just swing this one down. So this point here is -4 pi over 6. You still have your x and a y on the graph. Cool? Of course, right? It's math. No problem. No problem. The question now is, well, hold on. We have x and a y, and that point is given in these new polar coordinates. Does it have it xy coordinates? And the answer is yes. We just have to convert this So now we want to learn about the conversion between polar and rectangular world. And there are two sets of two formulas, obviously, and you can either memorize those or you can derive them very simply. Let me show you the way to get this. So you have your standard xy, and you have a point, let's say right here. Now that point is at the same time some xy and r theta, right? So you have your triangle. To get there, this is your angle theta, this is your r, this is your y, this is your x, and all you need to do is to write three trigonometric functions for it, and the fourth equation is the Pythagorean theorem. You know all four, right? And those four will be your equations for conversion. If you write sine theta is equal to opposite over hypotenuse, you see that you have r and theta in this one, right? Which means that since you have r and theta, then you are calculating y. So you will solve this one for y, and you will get y equals r sine theta. If you write a cosine equation, it will be x over r, because it's adjacent over hypotenuse. Again, r and theta are present in the equation, so you can compute x because r and theta are both given to you, so you can calculate x. And these over here are already a pair of equations which convert polar into rectangular, because each equation has both polars given, and you calculate one rectangular at a time. If you write equation for tangent theta is opposite over adjacent, so that's y over x. And you see that you can calculate theta if you use inverse tangent of y over x. And finally, r squared is equal to x squared plus y squared Pythagorean theorem, which allows you to calculate r if you take a square root of x squared plus y squared. Now, before you scream, what happened with the negative, plus minus, right? R is a length, so we don't need it. And this over here is the second set of equations, which converts rectangular into polar. Rectangular into polar because you feed two rectangular coordinates, and it spits out either the angle or the radius. So now we have two sets of equations which would convert between the two worlds. Do these worlds compete? And the answer is no, they don't compete. They are each very useful in their domain of effectiveness. Polar coordinates are to be used for situations when you have circles and rounded figures. We are going to see that. Where rectangular coordinates are great for rectangles, squares, and triangles and things like that. We know that integration is done in rectangular coordinates to find area under the curve. Well, in polar coordinates, it's going to do the same thing, except on different type of geometry, which you haven't figured out so far, haven't seen most likely so far. You did see circle, obviously, but you haven't seen the other stuff that it's coming up. So now, what I wanted to say here with the competition between the two worlds, generally, what's nice and pleasant in one coordinate system, it's going to be absolutely disgusting in the other one. That's usually the way it goes. And here are the examples why, and how. Just take a basic point, let's say 3, 8, right? 3, 8, you can graph that in rectangular system, right? You go 3 on X and 8 on Y. You can, right, solve that, get that point. To convert that into the polar system, really, right? Because your R is going to be square root of 3 squared plus 8 squared. Like, okay, good luck there. The inverse tangent is even going to be worse than this. So now we have a square root of 9 plus 64. It's a square root of 73. Great, that's your R. And your theta is inverse tangent of y over x, which is 8/3. Yeah, good luck there, right? So you understand that, you have no issues with 3, 8 in rectangular. But look at the polar, right? Now, flip the coin and take something nice in polar, just like 3 and pi over 6. It's great. You know that you draw 3 and then 30 degrees up, right? It's very simple to deal with it. And then you say, yeah, but I really like rectangular. Well, great, good luck. X is r cosine theta. That's 3 times cosine of pi over 6, which is 3 times, yeah. So good luck with this. You see that? I.e. not beautiful, right? And then your y is somewhat nicer. 3 sine pi over 6, which is 3/2. But still, right, 1.5. So these two systems do not compete. What works great in one is not going to work nicely in the other. And they both have their domain of effectiveness, which is why it's important to know them both. It's not one of those things, yeah, I know rectangular, so I don't have to bother. You actually have to bother because polar systems are going to give you polar coordinates. They're going to give you double integrals in polar coordinates and eventually give you rise to something that's called cylindrical and spherical coordinates in Calculus 3 when you move to the 3D coordinate system. So a lot of Calc 3 will be depending on these or built up on these to go one dimension higher into 3D. So you have to know it. The next, so far we understand a single point. We understand how to graph those points no matter what we get. And we understand that if we need to, we can convert those points into our good old XY realm, right? Now, the next question is, what is happening with functions in polar coordinates? Now, guys, this is still part 1 because we are not doing calculus yet. Once I start talking about derivatives and integrals, then we are switching to 12.3, which is calculus. So functions in polar coordinates. Well, I'm just going to, take a little box over here on the side and say, remember that y is equal to f of x, right? Where x is your input and y is your output, right? So that's good old stuff. Now, in polar coordinates, you have r as a function of theta. And this is something that if you are going to Calc 3, if you are thinking about mechanical engineering, this is something that you absolutely must understand, the way these things work. They're not the same as your rectangular systems. R equals f of theta. And now what you have here is your input. So this is instead of your x. And R is your output. So to give you an example of this, I can say R equals 3 theta. R equals 3 theta. So now the question is, what is this, right? You know that if you had y equal 3x, yeah, it's a straight line. Awesome, right? Now, what is r equals 3 theta? Well, you have to figure it out. And the way to figure it out is going to be the... Yes, very good. It's a spiral. Awesome. The way you figure it out is you, just like you did in the middle school for x and a y, you pick x's, you compute y's, and you see what comes up. Over here, you assign thetas, you compute r's, and then you have r comma theta, you plot those points, and then connect them, right? Connect the dots. You don't have to color, right? That's a plus. It's just connecting the dots. All right, so theta and r. Pick some thetas, let's say 0, maybe pi over 4, maybe pi over 2, maybe pi, 3 pi over 2, I don't know, right? You just pick some of these. Okay, let's pick 2 pi as well. There you go. When I plug in 0 for theta, 3 times 0 is 0. So I computed 0 on the other, and I can draw the first point 0, 0, which would be at the origin. Now I'm going to pick theta to be pi over 4. Now pi over 4 is about 0.7, right? Right? If your pi is 3.14, divide that by half, you get about 3.57. Divide that by half, you get about 0.707. So this is roughly 0.707, I think, or something like that. And you multiply that by 3, and you will get roughly 2.1. So now, at pi over 4, you will go 2.1 and swing, and you have your second point. Pi over 2 is about 1.5 times 3 is about 4.5. So, since that's pi over 2, that's actually y-axis. So 1, 2, 3, 4.5 is the third point right there. Pi is 3.14. Well, so 3.14 times 3, that's about 9.5. So we will go over here and look for 9.5. 2, 3, 4, 5, 6, 7, 8, 9.5. So this is for your pi over 4. This is for your pi over 2. This is for your pi. And now, when you connect these dots, right, you are going to get a spiral, and this spiral is going to go out. Now, when you think about this, right, it's going to go like that. That's not going to be a function, right? So if you think about a regular spiral that you draw, in an arts class or whatever, like that, right? If you cut this, not in the arts class, in math class, when you cut this with a vertical line for the vertical line test, you see that this fails miserably to be a function, right? Well, let me rephrase that. This fails miserably to be a function in rectangular coordinates. In polar coordinates, it's just fine. You see that? Can you even imagine the equation for this in rectangular coordinates? Yeah, we're going to find it now. And you want to integrate, right, or differentiate? No. But look up there. You just have to deal with 3 theta. How hard is to differentiate or integrate 3 theta? It's a joke, right? So what I promised before, right, what's beautiful in one coordinates is going to be absolutely disgusting in the other one. So let's just convert real quick r equals 3 theta to rectangular coordinates just to prove the point. R is replaced by the square root of x squared plus y squared times 3 times inverse tangent of y over x. There's your conversion. Can we write this as y equal everything else? No, we can't, right? I mean, you can apply tangent to both sides to kill that inverse tangent, and then great, you're just going to have tangent of a square root there, and you're going to have, right, 3y over x. There is no way. There is no way to write this in implicit form and have a nice function in rectangular coordinates. So this is what we have, and this is the reason why we want to learn both systems, right? I would rather deal with r as 3 equals 3 theta than with this line here with all of this mess in there. So now, question is, what are our basic functions? Or basic lines, or whatever. If we go, again, here's the box, remember. And I have to do this because elementary algebra was years ago, right? Remember, for elementary algebra, that in your xy coordinate system, the most basic lines that you can draw were x equals a number and y equals a number, which were vertical and horizontal line. So if you have your vertical line going through this value here, let's call that value a, the equation for this line was x equals a. If you had a horizontal line like that, going through value b, your equation was y equals b. Those blue and red lines eventually became your horizontal and vertical asymptotes, and you had all other fun with them. But those are the most basic. Y equal a number, x equal a number, right? Everything else is more than that, like y equals x. That's a 45-degree line. It's a still straight line, but it's at a 45-degree angle, right? So now the question is, what are the basic functions or lines or curves in polar coordinates? So clearly, one of them is going to be r equals a. So what is r equals a? Circle. Excellent. Please observe that, pick any line, I don't care, blue or red. If you look at the blue line, do you see how equation y equals b does not mention x at all? Because x takes on all of the values from negative infinity to positive infinity, right? And x is not mentioned in that equation at all. Well, theta is not mentioned in this equation at all, and theta is going to take all of those values at the same time. So what this is going to graph is a circle with radius a. No matter which angle you pick, it will always give you a circle. I'm sorry? It's years of So r equals a is going to give you a circle. Now, as the alternative aside, let's go green a little bit, is going to be an ellipse, because that's the actually the general shape here. And that one is going to have A and B. And you can't really do this nicely in polar coordinates, but for parametric you saw, you can do a lot, right? So we don't want to deal with ellipse in polar coordinates. We don't want to deal with an ellipse because, and so I'm just going to put it like this and say we use parametric equations here. And the last class we learned that x equals a cosine theta and y equals b sine theta. So we don't use polar coordinates to deal with the ellipse. Can we? Yes, but why? Parametric equations are going to deal with it like this, so don't worry about it, right? Another basic one that we can draw is theta equals a number. Theta equals b. Now what is this going to give me? Straight line through origin. It's always through the origin. So now, if I draw this situation, I'm going to have a straight line with the angle theta. It's infinite line in both directions. And it's going to be line through origin. Can you go outside of the origin with a straight line? Yes, equation is going to introduce secant. So good luck, all right? So your equation for a straight line in polar coordinates, if it's not going through the origin, is going to have secant in it, or cosecant. Why so ugly? Because polar coordinates are supposed to be dealing with curves, not straight lines. So the straight line is through the origin is the only one that you can get for free and easy. Everything else, not going to be nice. So theta equals a value, a number. Theta equals b. So an example, theta equals pi over 6. Theta equals pi over 6 is just going to be a line that it's at 30 degrees going forever in both directions, right, to the left and to the right. So those are your basic functions. Now the question is, all right, so there is a circle. We don't like to deal with the ellipse. The straight line, just the basic one through the origin. We kind of stay away from everything else. So what actually are these polar graphs all about, right? We saw the circle. That's awesome, right? R equals 3 is a circle, radius 3, so it can't have that easier than that. But what kind of functions can we expect? Now, guys, again, you're supposed to explore here. This is completely new to you. You never had polar coordinates before unless your teacher in Pre-Calc2 touched upon it a little bit. Some do. And since you have zero experience with this and a lot of Calc 3 will depend on it, playing on the calculator, your TI 80 whatever, is crucial. So I am going to spend some time talking about your TI 80 something friend, whatever you have. Generally 83, 84 is what you guys have, and most instructions obviously are there for these calculators. So if you have one right now, great, bring it up. If you don't have it, don't panic, because I am going to use this document camera I have here to project. Now it's not going to be on stream because this goes through the computer here. I'm going to give detailed instructions on how to use the calculator, and I hope that you guys will practice these things so you can see them yourselves. Now, first of all, or if you have a good phone, none of that Apple garbage, you can install these calculators on your phone through the app, and then they have all of them from 82 to 90, whatever is the latest one, and you can just use it on the phone. Now, you know that these graphing calculators are not allowed on the exams, so this cannot help you on the final, but it will help you a lot to get your bearings straight with this. So I hope that my battery is strong enough here. So let's see what we have. Full screen, camera, and perfect. Oh, maybe if I push the button. Okay. So now you are staring at the blank TI 8384 screen. The first thing you have to do is to push the mode button and make sure that you are in radians, otherwise it's not going to work. So we're going to push mode button, and we're going to go down to radian measure, and then in the next row you see POL. That's your polar. Okay, you will click polar to select. So function is x and y graphs, parametric, polar coordinates, sequences. So your calculator can be in any of those modes. So you must be in float, radian, polar. That's it. Now when you hit enter on polar, second quit, and go back to the main screen. Now, I forgot to clear my calculator, so I don't want to. There we go. All right, so now, when you go and push your y equal for graphing, you don't see F1, 2, 3 like you used to. Now you see R1, 2, 3, right? Because the functions are R equals. And we want to type an equation. So if I go and I say R equals pi divided by 6, when I push the graph button, I need to see circle of pi. R equals pi or 6 is R equals 6. Clear this. R equals 6 and graph. I wanted to graph a circle. Now you're going to say, hold on, that's an ellipse, because the screen is not a square and they have 10 by 10 by 10, right? If you make your x-axis and y-axis, you can play with it to get this to look like a circle, but you can see that there are 6 tick marks in each, right? So it's squished because the way the screen works. Okay, cool. So now we have that. Now let's take a look at something nicer. So let's go with 4 cosine, and let's put 4. Now guys, on your calculator, I hope you use that x for your variables, right? Now you see it has theta? So that's your variable. You will push that x to print theta. And it prints theta. You close the parenthesis. Now, you are going to go push enter to the next line. And now you're going to go and say window. Right? Now, on this window, we are going to just change real quick. We're going to change x minimum to -4 and x maximum to 4. Leave the scale at 1. And then for y minimum, put -6. And for y maximum, put 6. That's it. That's all we're changing. So x minimum -4, x maximum 4. Because I don't want it to be distorted, like, you know, that circle looks like an ellipse. And now it's time to push the graph. I did it backwards. Back to window. X coordinates need to be -6 and +6. Well, that ruined it. Rip. -4 and 4. There we go. Graph. Much better. Cool, right? So that you get the flower. Now, R equals 4 cosine 4 theta gave you a flower with 8 petals in there. Flower with 8 petals. And observe that it stretches out to 4 because it was 4 cosine theta. Now, this is the way you are going to learn and play with these things. You go back to y equal and then change the 4 petals into 2 petals, into 2 theta, sorry. You will see that you now have 4 petals. And then you might say, oh, so that's double. I plug in 2, I got 4. I plug in 4, I get 8. Right? So it seems that it's double. Then you go back and you plug in 5 theta. And when you push enter, it will give you 5 petals. So this is where you learn that if the number is odd, it will have that number of petals. If the number is even, it will always give you double amount of petals. Right? Then you are going to go back to 4. Now, back to 2, so that you can print your 4 petals like this. And then you say, okay, if I swap with a different trig function, if I put sine, what would happen? So you go again, you go here, and you replace the sine instead of cosine. You push graph, and you find that your circle is now rotated a little bit, right? And then you start playing with these things. What do I get if I do this? If I do that, right? And what happens if I clear this and I just put sine theta, close the parenthesis, and put -1? Like, what is this going to do? Graph. That shape is called cardoid because that shape looks like a heart. And it's not a perfect heart, right? The way you want to, and actually this looks more like a real heart than what you draw with those spikes, right? Because if the real heart had that spike that you draw, that will poke through other organs and you die, right? The real heart is rounded like this. Do we have any biology people in here to help me out with this, right? So there are a lot of these shapes, right? Some of those are listed in a book, and I can't teach you any of that stuff. You have to sit and say, I want to learn these things, and keep poking on the calculator and ask yourself what changed. What if I do +1? What is that going to do, right? So you go back and you say, okay, that was a -1. What if it's a +1? And then graph. Great, nothing changed. Right? So, these are the things that you will be trying to figure out. And as you go through your study time. And Now, if we go back to, let's say, r equals 4 sine 2 theta, and we said that's going to be a sideways flower like this. Once I have this sideways flower, what do I have? I have area to color. That means I should be integrating this to find the area of each petal. Now you say, who cares? It's just a flower. You know, give it to show the affection and be done with it, right? Yeah, but these might be the blades of a propeller of some kind, in which case you definitely want to know the area, because then you are pushing air to propel either your boat or your airplane, which makes sense, right? So all of a sudden these flowers become, you know, things that we build. And there are also tangent lines, which means some derivatives will be involved as well. So that opens doors to calculus, and that's when we all get excited, because it's calculus class, right? So now we get to do some of some of that stuff. And this is where we kick in with calculus portion of the lecture. So calc of polar, or calc with function, well, yeah, whatever. Calc of polar functions. And we ignore the limit, unfortunately, such is life. We want to know about derivatives. Now remember how I said that the straight line, that it's not going to origin, is absolute living nightmare? We don't really want to find tangent lines in polar coordinates. We want to find the tangent line with the regular y equal mx plus b, but of the polar equation, which means that we are supposed to somehow figure out the formula that computes the slope using polar world, but give us the answer in the rectangular xy world, and then we can just deal with the plus b situation and we are done. It's not as easy as it sounds, because we have to derive the formula. Now, what do I have? I have some function r f of theta. And here are the examples, right? Those are the functions. I can write this as f of theta is equal to 4 sine 2 theta. That's the same. Just like you can write y equals x squared or f of x equals x squared, right? It's the same meaning. You either use y or use f of x. So now you can use r or you can use f of theta, because they mean the same. But your slope m is equal to dy dx. And you don't have any x's and y's in here, and you don't want to convert it either. So how do we deal with this? Well, the cool way is to change this, multiply top and bottom here by 1 over d theta, like this, which gives you that parametric form of dy d theta divided by dx d theta. And we know that y is equal to r sine theta, and r is actually some function of theta times sine theta. So now I need the derivative of this so I can plug it in here. And then I have to repeat the whole thing for dx. So dy d theta is, hey, that's a product rule, right? You have one function in respect to theta and another function in respect to theta. We get to do product rule. Yay! Copy the first times derivative of the second plus copy the second times derivative of the first. Awesome. Rinse and repeat for x. X equals r cosine theta, which is f of theta times cosine theta. dx d theta is equal to product rule again. Copy the first, derivative of the second, plus copy the second times derivative of the first. That one has a minus sign. So let's list that one second. But if I'm going to put f prime to be the first, then I'm going to put the f prime to be the first on the other one. So my dy dx, which is in the rectangular realm, is going to be f prime theta sine theta plus f of theta cosine theta divided by f prime theta cosine theta minus f of theta sine theta. And there is your derivative in x and y domain using only the polar input. Who's excited? Thank you. Now, find the tangent line at theta equals pi over 4 for r equals 4 sine 2 theta. This was the flower we had that was at the angle. Okay? So you want to find the tangent line for this one. Well, all you need to do is to plug all of this up there and take some derivatives. So you already have your f of theta, which is 4 sine 2 theta, right? Because we know f of theta is r. What's f prime of theta? 8 cosine 2 theta. Perfect. Yeah. The derivative of sine is cosine 2 theta, and then the chain rule will kick 2 outside. 2 times 4 is 8. So I have f of theta, and I have f prime of theta. Awesome. It's time to plug those f and f prime in the function up there, and then in the formula, and then replace every theta with pi over 4, and that will give you the slope 30 minutes later. So we have that the derivative dy dx is equal to 8 cosine 2 theta times sine theta plus 4 sine 2 theta times cosine theta divided by 8 cosine 2 theta times cosine theta minus 4 sine 2 theta times sine theta. Lock the doors. M is when you compute the derivative at theta is equal to pi over 4, because that's where they want us to compute the tangent line. Well, awesome. Just plug in pi over 4 everywhere. So 8 cosine, hey, 2 times pi over 4 is pi over 2. And then you have sine of pi over 4. But cosine of pi over 2 is 0, so it's going to kill the term. Plus 4 sine of pi over 2 cosine pi over 4. That's going to live. Divided by 8 cosine pi over 2 again. Cosine pi over 4 minus 4 sine pi over 2 sine pi over 4. So whenever you see pi over 2, that's because we had to double it because of the formula, 2 theta up there. So 2 times pi over 4 is pi over 2. Now, these terms will go to 0 because cosine of pi over 2 is 0. That kills everything there. So m is equal to 4. Sine of pi over 2 is 1. Cosine of pi over 4 is root 2 over 2. Divided by negative 4. Sine of pi over 2 is 1. And then I have another root 2 over 2. Do we all see that the slope is negative 1? Negative 1. Now, you shouldn't be expecting anything else because the pedal was right there, and that's where the pi over 4 is, and the only tangent line I can draw there is this one, which is perfectly at the negative 1 angle, right? This is what everyone says, right. And then we move on. So now we calculated slope of m equals negative 1, and the only thing that is left is to find b, value of b, because we have y equal mx plus b, and for this to happen, I need my x and y. But all I have is theta is pi over 4. And I have r, which is 4 sine 2 theta, right? So I have to use these two to come up with a point. So I can plug in this one and get r equals 4 sine of pi over 2, which gives me a 4. So now I know that my point in polar coordinates is 4 pi over 4, and now I have to convert that into xy point. So what do I have? X is equal to r cosine theta, which is 4 cosine pi over 4, which is 4 times root 2 over 2, which is 2 root 2. Y is r sine theta, which is 4 sine pi over 4, is the same. So the beautiful point 4 pi over 4 turns into this demon with square roots. But that's okay. We can deal with that. I have m. I have x and a y. We have enough to calculate b. Y equals mx plus b. Y is 2 root 2. M is negative 1. X is 2 root 2 plus b. When you move this one to the left-hand side, it will add. So we have that b equals 4 root 2. And my tangent line is y equals negative x plus 4 root 2. Cool. That's how you do derivatives. I mean, for tangent line. The basic derivatives are the same because you are only taking the r prime. So, I mean, yeah, r prime. You'll be sick of r prime once Calc3 kicks in. It's going to measure velocity as well. So it's going to be a lot of that. This is tangent line at pi over 4. It's very important because if I change that to pi over 6, you start this calculation from scratch because you will plug into derivative pi over 6 or whatever, pi over 3 or whatever else. You will come up with a different m, and then you have to go through everything. I guess we'll have to leave integrals. Well, we can at least start integration with a formula. And then we'll do more examples on Monday. Integration. To find area, you have 1/2 integral alpha to beta of f of theta squared d theta. This is the integral formula that will compute area inside. Now, to understand this little bit, I'm going to draw a circle here and do the pizza slice from angle alpha to angle beta and shade this region. This function here is your r, function r, which is f of theta. That's the one you are squaring. Alpha and beta are angles because these limits are now angles. You see what the input is here, right? When you had x, those numbers were a and b, x1 and x2, right? Cut off on x-axis. When we had sideways integrals, they were y1 and y2. Now in a polar world, your input are angles. And the theta goes from alpha to beta. Those are the first two letters of Greek alphabet, right? So we use alpha and beta for angles, and then a and b for x values, and then c and d for y values. Now you are familiar with a, b, c, d because we had all of those integrals horizontally, vertically in chapter 6, so you're probably sick of that. Now you have alpha and beta. So a typical integral now would be area equals 1/2 0 to 2 pi of 4 sine 2 theta, but all of this needs to be squared. And what I'm going to calculate here is area of all 4 petals of that flower. You want only one? Well, you can divide it by 4 because you have 4 petals, right? 0 to 2 pi, because 0 to 2 pi are angles that will draw the entire flower. Now, I can also adjust how much of a flower I want. If I want 1 petal, now, depending on which way, see, graphing is important now. You are not guaranteed to have a petal from 0 to pi over 2.
Why is the 1/2 there?
That's a longer story. Because in the polar coordinates, you know that the domain is 2 pi. For sine and for tangent is just a pi. And so it has to do with that stuff. I can tell you later, because we have negative 30 seconds left. So So now, as you are integrating this, guys, you see your old friend come back, and that friend is called power reducing formula, because now you have this sine squared there to deal with. So reviewing power reducing formula, not just for your trig integrals that you will need for your final, but also for integration that we are going to see next time. What kinds of integration we can get? Well, remember area between two curves? Yeah. What if I inscribe a flower into a circle and ask for the area of the negative space, right? What if the circle is one size and the flower is peeking out? What's the area of the difference of how much is peeking out? What if I intersect the cardioid you've seen with the circle or the flower and the differences between those, right? So that's the stuff that we are going to cover next class, and then have the review and be done. Bye.